This is the fourth lecture in the Chemical Reactions and Chemical Equations unit. In this lecture, it would really be helpful if you would get out any help sheets that you have. Hopefully you've got the help sheets that go along with this unit. Get out a periodic table so you can have it handy. And if you're taking notes, make sure you're ready to do that. So we've been looking at types of chemical reactions, patterns that chemicals follow. We saw decomposition and combination reactions, which are the opposite of each other. And in the last video, we looked at single replacement pattern. In this video, we're going to do something similar to single replacement, but we're going to call it double replacement reactions. So a double replacement reaction is just like a single replacement, except that we don't have any elements by themselves. Instead, two of the elements from two different compounds are going to trade places. Here's an example. Silver nitrate can react with potassium chloride. What you do is pick any of the ions. I always use the metals personally, and swap places and then write neutral formulas for the resulting compound. So the Ag is a silver ion, the K is a potassium ion. Those are both metals. Let's change places. We're going to get potassium nitrate and silver chloride. Now in this particular example, the Ag has a +1 charge, the K has a +1 charge, so when they switch places, no new subscripts, no new coefficients are necessary. This is the balanced chemical equation for the replacement reaction between silver nitrate and potassium chloride. There's the ion charges just to show you that we do have neutral formulas written on the right hand side, but you always got to check that. One of the help sheets that goes along with this unit looks like this. These are the water solubility rules for ionic compounds. Now these are not 100% foolproof, but basically this will get us through this unit. If you just follow the rules in order, when you're given a compound, check both ions and see if they fit rule 1. If either one of them fits rule 1, that compound will dissolve in water. If neither of the ions are in rule 1, check rule 2, and then so forth. Just do the rules in order. Now the reason why you have to do this is, in order for a replacement reaction to take place, one of the compounds that results must be insoluble. It cannot dissolve in water. So if you write two formulas and both of them fit rule 1, for example, then that reaction actually does not take place. Those ions will just stay dissolved in water and will come right back apart. We're looking for an insoluble compound. If it's a solid, then we will call it a precipitate. It will fall to the bottom of the reaction vessel, the test tube, for example. It could be a pure liquid like water. If it's a covalent liquid compound, then a double replacement reaction can take place. Or if one of the products is a gas like carbon dioxide, then that replacement reaction can take place. But you have to have a product that is either insoluble, a liquid, or a gas, or else the reaction doesn't happen. Just because you put two chemicals together does not mean that they will react. If it's not already written on your help sheet, you may want to write, use these water solubility rules for double replacement reactions. And make sure that you use the rules in order. If either of the ions fits rule 1, then apply it. If rule 2, then apply it, and so forth. So in our particular example that we just did, if you look for potassium, which has a alkali metal, you'll see that it follows Rule 1. If you find nitrate, in fact, it's also in Rule 1, so both of them follow Rule 1. It doesn't matter if both do as long as one does. So potassium nitrate is soluble. That means we would write an AQ after it. These reactions take place in water, and so the potassium nitrate will actually be dissolved in the water. But you do not find silver, which has a +1 charge, in Rule 1, and you don't find chloride, which has a -1 in Rule 1. We do see things that have chlorine in it, like the perchlorate on the end of Rule 1, but you don't see chloride by itself. You do see silver in Rule 2. So the silver chloride will not dissolve in water. It's insoluble. So you don't write AQ. It will actually turn into a solid precipitate. We're going to write S for solid. So this double replacement reaction will occur because one of the products is insoluble. Here it is in cartoon form. We see Fred and Wilma, and then Barney and Betty. So if we swap Fred with Barney, we get a double replacement reaction. Now Barney is with Wilma and Fred is with Betty. That's kind of strange. So the general form of the double replacement reaction can be seen to be as follows. We have two ionic compounds that are dissolved in water. If a reaction occurs, then one of the products will be an insoluble compound, either a solid, a liquid, or a gas. The other compound will still be dissolved in water. It actually won't even form. The ions will just stay in the water. But in order to figure out whether or not you get an insoluble precipitate, follow the water solubility rules. In letter form, we might show the pattern something like this. Compound AB reacts with CD. The A and the C swap places. We always keep the positive ion first, so it will be CB plus AD are the resulting compounds. One of those, it doesn't matter which one, but one of those, either CB or AD, has to be insoluble. Of course, when you write the final pattern, you should erase all the charges. We don't show charges in neutral formulas. Here is another example of a potential double replacement reaction. I say potential because we have to check the products to make sure one of them is insoluble. So we have lead nitrate. That lead must be lead +2 or lead 2 because there are two nitrates which have a -1 charge. So that's lead 2 nitrate dissolved in water reacting with sodium chloride dissolved in water. The lead and the sodium are going to swap places. And so we will get sodium nitrate and lead chloride. Now the sodium has a +1 charge and the nitrate has a -1. So that formula is already written correctly. It is neutral. But the lead had a +2 and the chlorine is -1. We're going to need another chloride ion. That's PbCl2. And now that's going to require some balancing. But before we balance, before we go to that trouble, we better make sure that one of these products is insoluble. So let's go ahead and look at our. So here's our solubility rules, and we wrote the compounds down again. What we're looking for is to see whether or not either of the ions in these compounds fits one of these rules, and we follow the rules in order. So first let's start with the sodium nitrate. Let's look for sodium and nitrate, either one in Rule 1. Turns out that both of them are in Rule 1. Either one would have been sufficient. That means that this compound dissolves in water, and so we are going to write AQ after it in our equation. That's not what we're looking for. We want a compound that does not dissolve. So we're going to write AQ after NaNO3. Let's go back and the lead 2 chloride. Do you see Pb2 or Cl- in Rule 1? You do not. But you do see Pb2 in Rule 2. That means compounds that have that ion do not dissolve in water. That means an S after it, which means it will precipitate, and it means that this reaction can proceed. If you write AQ for both of the products, there is no reaction because all that actually happens is the ions stay dissolved in water. They're just running around. They may join with each other temporarily, but then they dissolve again. But if one of them becomes a solid, it will fall to the bottom of the test tube and react no more. And so this reaction can proceed in a one-way direction. Here's another example of a double replacement reaction. We got potassium sulfate reacting with barium nitrate. Now the potassium and barium are going to exchange places. Our new products are going to be potassium nitrate and barium sulfate. It doesn't matter which order you write the products in. The K is a +1 and the nitrate's a -1, so that is a neutral formula. The barium is a +2 and the sulfate's a -2, and so that's a neutral formula. We will need to balance this, but before we do, let's go and check and see if one of these is insoluble. So first we look for potassium or nitrate, either one, in Rule 1, and sure enough, both of them are there. Say potassium is one of the alkali metals. You may not see it listed there, but it's an alkali metal. So potassium nitrate follows Rule 1. It's always soluble. We're going to write an AQ after it. What about barium sulfate? Well, I don't see Ba2+ or sulfate 2- in Rule 1 or Rule 2 or Rule 3. I don't even see it in Rule 4. There's an S2- and an O2-, but it's not SO4 together. Now I do see sulfate in Rule 5, and my first glance says Rule 5 soluble, and I go, oh, that means barium sulfate is soluble. But you always have to read the exceptions. Look at that. Barium sulfate is insoluble. That means I will be able to write an S after it. It will precipitate. This reaction can proceed. So this is a good double replacement reaction, so I might as well balance it now. I see 2 potassiums on the left, only 1 on the right. So it's time for a little practice. Here are 2 sets of reactants. I want you to predict the products, write their neutral formulas. Check the water solubility rules and see if one of the products that you predicted is insoluble. If so, write an S after it, then go back and balance these equations. Please pause the video and actually try these on your own. When you restart the video, I'll go over the answers. Here's our first equation. Hydrochloric acid and silver nitrate react. The hydrogen in the hydrochloric acid is acting as a positive ion, so it's going to swap places with the positive silver ion. So we're going to get silver chloride, and hydrogen with the nitrate makes nitric acid. Since both the hydrogen and the silver had the same charge, you don't need to change any of the numbers, and this equation will be balanced as is. Now if you check the water solubility rules, you'll see that the silver chloride is insoluble, and so this reaction can proceed. So I just gave away the answer, but let's go and check the activity list. You'll find that the nitrate in the nitric acid fits Rule 1, and so that is always soluble, so we're going to write AQ. It will stay dissolved in water. But the silver +1 fits Rule 2. It's not found in Rule 1, and chloride is not found in Rule 1, so Rule 2 applies. So the silver chloride is a insoluble solid, it will precipitate in this reaction, and this is a valid double replacement reaction. For a second example, calcium chloride and sodium phosphate react. Sodium and calcium swap places. We are going to have to rewrite the formulas. Don't carry the subscripts across unless they're part of a polyatomic ion. Instead, you need to think about their charges. So the sodium chloride, for example, that is a good formula because sodium is +1 and chloride is -1. The calcium phosphate is not CaPO4. The calcium has a +2 charge and the phosphate has a -3. So to neutralize that, we are going to need 3 calciums and 2 phosphates, +6 and -6. So the correct formula for calcium phosphate is Ca3PO4 with a 2 outside the parentheses. If you check the solubility rules now, you'll find that the sodium ion in sodium chloride is always soluble, so it fits rule 1. But the phosphate ion is insoluble, and so that is going to become a solid, and so this is a valid reaction. Now we need to balance it. We see 3 calciums on one side and only 1 on the other side. That might be a good place to start, so let's put a 3 in front of the calcium. That gives us 6 chlorines, so we need to put a 6 in front of the sodium chloride. That means we now need to put a 2 in front of the sodium phosphate, and that should balance it. So there's your final answer for the double replacement reaction between calcium chloride and sodium phosphate. It's time to practice. There should be a worksheet that accompanies this video. If you don't have that, then I'm sure your teacher will supply you with a couple of problems to see if you can predict the products and balance the equations, and make sure that one of the products is insoluble. Use those water solubility rules.